All right. I don't know what it's been. I don't know what's going on, but I've been a little cranky lately. I don't know why. But trying to get over that. I don't know. I don't know what it is. Not myself. I want to tell you. I want to share something with you that it has to go along with the whole homework thing, but it's really cool because it also connects with something that I did this summer. I worked on a research project this summer with five of my former students. It was really, really cool. And we spent 8 weeks this summer working on this project. And it was part of this company that I work for. It's called Blackthorn. I'm a software developer for them in Whitewater. I do Java programming. But they're spinning off on this other project, which is basically it's this. It's the program is a program that tries to work the stock market better, so you can buy and sell, and you can have an edge in buying and selling stocks. Okay, so it's a thing to make money, and what it does is it tries to make a prediction as to what's going to happen next. And then you can buy and sell based upon that. So it looks for patterns in data. And the data is like the prices of the stocks. Okay? So it looks for patterns in the stocks and says, ooh, okay, what do we think is going to happen next? And there's a lot of people trying to do this. But the research that we did this summer is the guessing part as to what's going to happen next. Okay? And let me explain how on earth this relates to you guys right now. The concept is the thing that we were studying was something called machine learning and neural networks. Okay, so machine learning is the big topic, and then inside of that is this thing called neural networks. Okay? It has actually a lot to do with artificial intelligence. Okay? Making decisions. And if you're into AP psychology, or if you've taken psychology and you're interested in that, you might find this very interesting. So let me tell you in kind of a simple way what we did. Think of times that you attempted something that may have been hard the first time, but then after doing it several times, you just got better at it. I'm thinking of riding a bike. Remember when you were a kid? Can you remember the very first time you got on a bike? I can. It was horrific because I ended up in the ditch. Okay? It was very, very scary. Skateboarding, snowboarding, cooking. Okay? You see what I'm getting at? There's lots of different examples of things that are kind of challenging to do, and the very first time you do it, it's usually an epic fail. Okay? Now, imagine this. How many different things do you have to do that you've done in your lifetime that your brain had to figure out how to do it the right way? You know what I mean? I gave a couple of examples. Give me some other examples, just random examples. What's that? Driving stick shift. That's a great one. First time, epic fail. First 10 times, yeah. Okay, that's a great one. Give me more. Tying your shoe. Okay, just takes practice to do it. Okay. Yeah.
This is kind of super random, and
Yeah.
maybe I'll show you study all, but it's a YouTube video of some guy, and I don't know where he watched it. It's a bike, and it goes the opposite of the way.
Yeah, I've seen that one.
And like he tries to get on a normal bike, and he's like falling over, and like people didn't like think it was real, and then
Yeah.
he got so used to riding it the opposite.
Right.
That just made me think of that.
A really, really good example.
Yeah, it's like he like switched the steering wheel and the tires so that when he goes this way, the bike.
Because he had to ride it correct.
Pedal bike.
To ride it correctly, he had to relearn.
He had to relearn how to ride a bike.
Right. Okay. So now, people have been studying this for some time, and they said, "Well, wait a second. The brain is really an amazing thing, and it can do lots of different things. So that must mean that to learn how to tie your shoes, or to ride a bike, or to ride stick shift, it must have to have just like millions of different formulas, one for each different skill." Almost like a different function for every single skill that you want to learn. You know what I mean? It's got to have like, this is how you do this, this is how you do this, this is how you do this, and it figures that out. So thousands and thousands of different functions, right? Incorrect. The brain only has one way that it learns everything. Okay? And what it is it's called a neural network. And this is how it works. It's really, really cool. Now, we can't visualize, you can't see inside your brain. So what they do is they draw pictures that model it. And so I'm going to draw a picture of a neural network. So each of these little things in this column represent inputs to your brain. Let's do the riding of the bike. Okay? So when you're riding a bike, think of all of the variables that have to go into riding a bike. Okay? It might be the kind of bike. Okay? It might be the terrain that you're on. We might have something else. Balance. You have to learn how to balance it, right? You have to steer it. All of these factors go into it. Okay? The way that your brain works, it's just fascinating, is that it has these nodes that we describe them as hidden layers. And this is all stuff that I learned this summer. And so each of these inputs actually interact with all of these nodes here, which sort of look at each of these things and analyze and determine, they get feedback then that goes back to them, and you get this complex neural network that looks like this, where every one of these is connected to every one of these. And these go back and forth. Okay? As you ride the bike, you're learning how to ride a bike, because it gives you feedback. It says, whoa, you're going too much to the left. Okay? Next time you ride, go a little bit to the right. Okay? Balance yourself a little bit left, balance yourself a little bit right, and so on. Notice that when you're on gravel, it might be different than when you're on grass or asphalt. This goes on and on and on, and every single time you ride the bike, your brain gets trained to know how to ride the bike. Okay? These then all go towards what we say an output layer, and the output layer for us would be successfully being able to ride a bike. Okay? Now, every single time you fall, it's handled in this correction phase where it says, okay, don't do that again. Okay? And so then your brain, for whatever reason, now knows, don't do that. Don't ride straight into a wall, because that doesn't work. Okay? And so then you don't do that anymore. Okay? So it's in this process, and the more times that you ride the bike, the more it's ingrained in you, so that it knows then, whenever you ride a bike again, it knows how to do it. That's why you hear the stories about the person who, like 30 years later, haven't ridden a bike, and they could just hop on a bike and ride a bike. Okay, it's like no big deal. There's even the phrase, it's just like riding a bike. Because a lot of people ride a bike when they're a kid, but then they maybe not ride it for a long time, and then maybe randomly they ride one, and they can do it. Which is really super weird because riding a bike is kind of complex. There's a lot of that has to happen when you stop and think about it. Okay? Now, this is the same thing that happens when you want to tie your shoe. You do it wrong, okay? It's correcting itself. When you ride stick shift, it's doing this. This is why you have the ability to do something that's kind of hard to do, even if you haven't done it in a long time, if you truly learn how to do it the first time. And it took multiple times in order to do it. You know, I've been trying to explain how important homework is in different ways. And then it hit me. It said it's the research that I did this summer that explains the whole thing. The purpose in homework is to do this phase in your brain. Your brain has to be trained to look at multiple situations so that when you come back to it, you have the ability to apply it to a new situation. Example, you hop in a car that's got a different stick shift. Different car. It's not the car that you know how to drive. But guess what? You know how to drive it. You get a weird looking bike that you've never ridden before. Maybe it's really high or low or whatever. But you're able to apply what you've learned because you've gone through this phase so many times that you can figure it out. That's the essence of it. It's right here. It's the fact that when you do your homework, so many times you've seen all the scenarios that now when it comes to the AP test in May, you're like, oh yeah, it's just like riding a bike. I can do it. I can do those limit problems because I spent all that time training my brain to understand lots and lots of different scenarios so that when I'm asked to do it again later on, yeah, no big deal. This is it. This is the brain's way of explaining how this actually works. Which then makes the 10,000 hour rule so applicable. Because if you do something a really, really long time, then you become an expert. That you have the ability to do it because you've almost exhausted. No one ever exhausts all possible cases. But you've done it to the point where you have it. And the cool part about this is your brain has this series of networks that allows you to do, this is how you learn every single thing. There's only one way that you learn, and it's through this. Isn't that interesting? So, anyway, the kids that I worked with are actually, they're getting published in a paper, a scientific journal, and they're doing a presentation of their work in Indianapolis next week. It's kind of cool. So it's good. It was Tom Compass, David Eben, Tom Schachman, Ryan Albert, and Owen Kirkaby.
They all work at
Yeah, I was able to convince Blackthorn that this group would be able to do some really cool stuff, and so they let me do it. And so I got to lead them, and they did all this really cool stuff with it. So
what are they publishing? What's getting?
they're the research of what a neural network is, and then we're applying it actually to this thing called Twitter sentiment, which is something we've.
Wait, did your company come up with that thing?
We didn't come up with it. We're applying it to
Okay.
our project.
Okay.
So it's kind of cool. So anyway, so that's it. No more talk about homework. Yeah, it was very similar, very similar. Okay. All right, well, let's move on. So today we're going to talk about an oxymoron. Oxymoron. What is that?
Jumbo shrimp.
Jumbo shrimp. Okay. Today we're going to talk about infinite limits. Okay. So the goal today in this assignment, in these problems, is to find limits where the answer can be either a positive infinity or a negative infinity, okay? Which we've done a bunch of those, but we're going to approach it from a little bit different way today. So here's the first one. Find me the limit as x approaches 2 from the left of 1 over x minus 2. So I guess we should have a process, okay? So I'm going to identify over here. Some people like a list of like things to follow, so let's do that. The process for finding a limit, okay? You see a limit, what do you do first? See if you can plug it in, okay? What allows you to plug it in? Yeah, it has to be continuous, okay, at that point. Okay. If we can plug it in, means there's no holes or asymptotes, we can just plug it in. Parabolas, lines, those are all continuous, so we can just plug them in. Okay, if that doesn't work, what do you do? Yeah. We can factor. Inside here also, don't we try to just visualize it? Okay, if we haven't done this already, we should just see if we can try to visualize it. Okay, if it's a graph that you can see, go ahead and see if that will help you to get to the answer. If that doesn't work, go ahead and try to factor. I'll say factor and cancel. And then you rewrite. And then technically, after you do this, you go back up here and see if you can plug it in. Because after you factor and cancel, you end up with a new function. And then so you just start the whole process over with the new function. Okay? All right. If none of those work, then what? This is when you punt. And if you're not allowed to use a calculator, what you're going to do, and this is what we're going to do today, we're going to analyze it numerically. Okay? So analyze it numerically. This is the general process that you would handle, how to handle any sort of limit. Okay, so this problem here, this is actually a relatively simple graph. We know our functions really well. So this is a shift to the right 2 units of our parent graph 1 over x, 1 over x. And so the graph is going to look something like this. This is asymptote here, 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 and here, right? 1 over x minus 2, this is the shifting of the graph, of the parent graph 1 over x. Now here we can look at it and determine what is the limit as the x approaches 2 from the left. Answer is we're coming in closer to x equals 2 this way, and the y coordinates look like it's going to approach negative infinity. So the answer to this one is negative infinity. Okay. Now, that one turned out kind of good. So let's take a look at another one. Yeah. Swivl, okay. Okay. Did it find me?
Yeah.
Just like go way to it.
Moved just enough?
It just doesn't like me.
Now we need a small drone that can fly around with the recorder on it. You can tell it to go wherever you want it to go.
Go ahead and go buy that one.
Okay, next one. All right, look at this problem. It's the limit as x approaches 3 from the left of x plus 2 over x minus 3. Okay? Now, this one is different than the one in the back because is this a modification of the parent graph 1 over x? Not quite, because it's got the x on the top. It's x plus 2 on the top. So this one's a little bit different here. Okay? But what I do know is this, and this is the key point for today's lesson. What I do know is that at x equals 3, because if I plug a x equals 3 in here, I get 0 in the denominator, and I was not able to cancel anything. So that means I know there's an asymptote at x equals 3. Okay? This is the key point of today's lesson right here. Now, since I'm approaching x equals 3 from the left, there's only two options. Only two options. Either this thing goes like this, as I get closer to x equals 3, or it goes like this. It only has one of those two choices. So the way that we test to see which one it is we plug in numbers that are close to it. In other words, see where we have x equals 2? We plug in x equals 2 and see what we get. So you imagine this as a table. If you plug in 2 into this, I'll say f of 2 is equal to 2 plus 2 over 2 minus 3. Answer is 4 over negative 1, which is negative 4. Which means at x equals 2, I get negative 4. So 1, 2, 3, 4, I'm down here somewhere. This may seem like the answer is going to be going towards negative infinity. But let's just get a little bit closer to see what happens. What if I did something like 2.9? 2.9 is really close to 3 coming in from the left. Notice what I get. On the top, I get 2.9 plus 2. And the bottom, I get 2.9 minus 3. So this gives me 4.9 on the top and negative 0.1 on the bottom. What's 4.9 divided by negative 0.1? Negative 49. But the most important part here is what? Not the 49, the fact that it's negative. This means that the closer I get to 3 from the left, this answer is getting further and further negative. That means that I know that the answer to this limit is negative infinity. Yeah.
Okay, this may be dumb, but I understand how to do this completely, but what if you start doing it, you think it's going to be infinity, but then you can actually factor it? And I mean, you no problem.
If you can factor and cancel, then you do this after you would factor and cancel.
Okay. So you have to go through all of, there's no easy way of telling, okay, this one.
Right. Because if you could cancel it, then you might have just a hole.
Okay.
And you want to, this doesn't apply when you got a hole.
Okay.
So you know the whole
Yeah.
accountable
Because you can't cancel.
Because I feel like I'm just going to start doing this to any sort of problem.
Apply those rules first. Boom, 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 boom. Go down that order. And then numerically, see what we're doing here? We're plugging in numbers. This is the numerical part. Okay? So let's try another one. Let's do one where we say, oh, okay, what do we got? Let's try this. The limit as x approaches 1 from the right of x squared minus 3x over x minus 1. x squared minus 3x over x minus 1. Okay. So again, you go through the process. Can you plug it in? Can you plug in 1? No, you get 0 in the bottom. Okay, no good. Can you visualize that one easily? Not so much. Can you factor this thing and cancel? Well, let's see. It looks like we can factor this, so let's do it. So this is the limit as x approaches 1 from the right of, I can factor that top, that's x times x minus 3 over x minus 1. So I factored. Can I cancel? No. That means there's no holes in this problem. Okay? There's only an asymptote. Where is the asymptote? At x equals 1. So, because the numerator is going to be 0 when x equals 1, then what we're going to do is, where we know for sure there is an asymptote here, and you can validate it by graphing if you wanted to, just to test it. And now let's approach 1 from the right and see what we get. We know we have these two possibilities. The answer is either positive infinity or negative infinity. And we're going to plug in numbers to figure out which one it is. Okay, so we're going to do a little f of. So let's plug in, I don't know, plug in 2. F of 2, what do you get for f of 2? 2 times negative 1 over 1. You get an answer of negative 2. Okay? That's close, but I'd prefer that you went closer. So let's do f of 1.1. That's getting pretty close. That's right here. So what do we get? We get 1.1 times 1.1 minus 3 over 1.1 minus 1. So 1.1 times, well, wait a second. 1.1 minus 3, that seems really hard to do. Yeah. Not really good at that math stuff, so. What's the most important thing that comes out of this? Positive or negative? Okay. The result of this, you see, is a positive times a negative divided by a positive. The result of this is a negative. And the only thing that we really cared about is this function going up or is it going down? And so I know it's going down to the right of 1. That make sense? We're breaking it down by looking at numerically what happens. So the answer there is negative infinity. That makes sense? Okay. All right, you do this one. Swivl. Got it. I don't think I'm ever going to get used to that. All right. My neural network, my neural network has to recorrect itself. All right, limit as x approaches negative 2 of x squared, and we'll go from the right this time, of x squared plus 2x minus 8 over x squared minus 4. I don't know. Does not matter. A bracket and a parentheses mean the same thing. They're just wrapping whatever it is. Okay, get me the answer to that one then. If you've never learned how to factor, you have to learn how to factor. Okay, did you go through this process? Bam, bam, bam. You get this. This is a new thing. Does everybody agree that when you look at this, since the x plus 2 doesn't cancel, that means that there is an asymptote where x plus 2 is equal to 0, which means x equals negative 2. That's a foundational thing. So, boom, boom, here's negative 2, asymptote here. And then now we're going to approach it from the right. So what kind of numbers should we pick? Negative 1 is 1 unit to the right. Okay, so that's a good one. So if I plug it in, I get negative 1 plus 4 over negative 1 plus 2, which is 3 over 1, which is 3. Okay, so it's positive. That doesn't give, it's not the giveaway though, because we might not be close enough. So what's a good number that's closer? Negative 1.9, okay, is close to it. So now we plug it in. Negative 1.9 plus 4 over negative 1.9 plus 2. Yeah. The only problem is if you have a graph that is, if it's shifted way up, okay, like this, it's possible that you could have a graph that, if this is what I've got here, the asymptote may be here, okay? So it's possible you plug in, I should put those backwards. Well, even here. Whatever. If you're, just because it's a positive doesn't mean that it absolutely is a positive.
No, but if you put it in two numbers, then, and their slope is negative, then it would be negative.
Okay, if their slope is negative between those two, then that's the difference. Very good. Okay, because that's the indicator. That's the separate indicator that you got. Okay, what do we get for an answer here? Positive and positive, so the answer is positive. So the answer to this is positive infinity. If you were to graph that thing, if you were to graph that thing, what we know for sure is that as x approaches negative 2 from the right, this thing would look like this. Oops. Other way around.
Did you mean to do that one?
No. So we know that it goes up. Okay? It's so good. You're not like zombies. Okay. All right, the last set of directions is pretty simple. You've done it before, so it's no big deal. The directions are find the vertical asymptotes. Okay? So here's a function. Here's a function. Tell me where the vertical asymptotes are for each one. All right, we play the game, let's make a 0. Okay, so you look at the denominator, where does that make a 0 without there being any kind of canceling? So x squared minus 9 is equal to 0. You can solve this either by factoring or by setting it equal to 0 by solving for x, either way. So that's where we get our two answers. This one has two asymptotes, one at -3 and one at +3. Boom. That means that the function is discontinuous at -3 and +3. Okay, it's continuous everywhere else, but it's discontinuous at -3 and +3. All right, so we play the game. X squared plus 4 equals 0. That turns into x minus 2, x plus 2. And we have two places where that's it. What?
It's plus 4, so they both have to be positive.
Oh, yeah, that's right. Doesn't this work, though? X minus 2 times x plus 2. Oh, that's right. It's x plus 2 times x plus 2. Okay. This is all garbage. Okay. Common sense. If I take a number and I square it, I'm going to get a positive number. If I add 4 to it, it's impossible for me to get 0. Okay? So different perspective says that, yeah, this can never equal 0. This function has no vertical asymptotes. Okay? Just make sure you give it back this time.
Yeah, Corey.
That was an accidental.
All right, do your homework. Your neural net needs it.